All right, so we're here to talk about quiz 7. We'll go over each of these problems. I'll write my answer out for you, so you can check your work against mine. If you have extra questions or need more clarification, send me an email, and we'll figure out how to address it. Either I can answer the question by email, or if necessary, we can set up a one-on-one Zoom discussion. All right, so question 1 is to solve this recurrence problem. This one is a homogeneous recurrence with initial conditions, so we are looking for one specific answer, one specific sequence that satisfies this. So our first step is we write the characteristic equation for this recurrence relation. So it's going to be degree 2, so we'll have r squared minus 2r minus 15 equals 0. So now we need to figure out what are the roots of that equation. So let's factor. That is r minus 5 times r plus 3 equals 0. So my roots are r equals 5 and r equals negative 3. So from that, we can get the general solution. So the general solution is the family of solutions, the family of formulas that satisfy the recurrence relation but don't necessarily satisfy the initial conditions. So the general solution is an equals alpha, let me use alpha and beta here, alpha times 5 to the n plus beta times negative 3 to the n, where alpha and beta could be any numbers. All right, so let me erase. That's basically half of the problem now. We've got our general solution. Now to get the solution for this specific problem, the formula that has these two initial conditions, I'm going to plug in the subscripts. So A0 is supposed to equal 1. Well, if I plug in 0 on the right side, I get alpha times 5 to the 0 is alpha, plus beta times negative 3 to the 0 is plus beta times 1. So alpha plus beta have to equal 1. Then if I plug in n equals 1, I'm supposed to equal 4. But that's going to give me 5 to the first power times alpha. Negative 3 to the first power is minus 3 times beta. Okay, so now I get these two equations with two unknowns, alpha and beta. I need to solve this system of equations. So let's see. If I multiply the first equation by 3, so just algebra now. Now we add, we get 7 equals 8 alpha, and beta, the beta terms cancel. So alpha equals 7 divided by 8. And then beta, well, together they have to add up to be 1. So if alpha is 7 over 8, then beta has to be 1 over 8. So my final answer then is an equals 7/8 times 5 to the n plus 1/8 times negative 3 to the n. That's my answer to this recurrence. All right, so then we've got non-homogeneous problem. So consider the non-homogeneous recurrence relation an equals 5 an minus 1 minus 6 an minus 2 plus some function f of n. We want to determine the form of the particular solution APN. So we want to determine what the function, what the solution looks like without actually figuring out its coefficients. Okay, so before we do any of them, before we worry about any specific f of n, there's 4 parts here, but before we do any parts, let's do the homogeneous consideration first. So we have our characteristic equation. Characteristic equation, it's degree 2 again, so r squared minus 5r plus 6 equals 0. That's r minus 3 times r minus 2. So my roots are 3 and 2. So that's not the answer, but that is necessary information to do any of these other particular solution stuff. Okay, so we don't care about the homogeneous part. We just care about finding the form of the particular solution. If f of n is n cubed plus 4n. All right, so the thought process here was what you want to do is write your function f of n as a product of a polynomial expression with an exponential expression. So if it's just a polynomial, like this one is, n cubed plus 4n, that's just a polynomial. The exponential part is 1 to the power n. Okay, so then, once you've written it like that, then you look, well, let's do it like this. Let's write the particular solution's form. What I want to do is, first off, I will try to exactly match the type of function I have. So by type, I mean it's a polynomial of degree 3 times 1 to the n. So I don't know the coefficients, though, so it would be a n cubed plus b n squared plus c n plus d. There's my polynomial of degree 3. Then I'll put a 1 to the n. I can erase it later, but because 1 to the n doesn't do anything. But I write the exponential part, and then there's one more question you have to ask. The base of that exponential part, is it one of our roots of the characteristic equation? Well, our roots were 3 and 2, so the answer was no. It's not. That means I'm done. My particular solution will look like this. Now here, let me remind you, this is not, it's not analogous to the general solution for the homogeneous stuff. It's not that I can pick any coefficients and it'll work. It's that I'm guaranteed that there will be at least one solution that has this form. To figure out what A, B, C, and D are, I would have to plug this formula into my recurrence and solve that resulting equation, or figure out the coefficients from that resulting equation. Okay, I'm not asking you to do that part here because that would be a lot of work. All right, so that was part A. Let's do part B next. Again, I don't want to erase the homogeneous stuff because that applies to all this. So same question, but now f of n equals 5 to the nth power. So APN is, well, again, we want to think of it as a polynomial times an exponential. This time I just have an exponential expression, 5 to the n. My polynomial then is just 1. So I want to match that. I want a degree 0 polynomial, so that'll just be a constant a times the same exponential expression. So a times 5 to the n. Then you have to ask the base, 5, is it one of our roots? And it's not. So this is APN. Okay. Next one, f of n equals n times 2 to the n. Come here, Meatsy. So we want to match this form with our particular solution. This time it's a degree 1 polynomial times 2 to the n. So I match that. Degree 1 polynomial would look like an plus b times 2 to the n. But then we ask, okay, the base is 2. Is that one of our roots? Yes, this time it is. So I have to adjust by multiplying by some number of n's. So I multiply by a power of n. And the power is the multiplicity of the root. Well, here 2 has multiplicity 1 because this is just a single factor, r minus 2. So it's n to the first power, which then I could simplify this as an squared plus bn times 2 to the n. That would be my particular solutions form. All right, one more of these. D is f of n equals 3n. So APN, again, we have to first break this up as a polynomial times an exponential part. There is no exponential part. See, n does not appear as an exponent. So the exponential part here is, again, 1 to the n. So this is very similar to part A. It's just a polynomial that I have to match. It's degree 1, so I need an plus b times 1 to the n. And the base, the relevant base is 1. 1 is not one of our roots, so we're done. It's just an plus b. The 3, the easy mistake here would be seeing the 3 and thinking that corresponds to the root. But this 3 is not an exponential base. It's just a coefficient. The thing we're comparing to these roots is the exponential base of our exponential part of our function. All right. So that's it for problem 2. Now we get to the fun one. See if this makes sense to me in the light of day. So now we have a counting problem essentially that we're going to solve using a recurrence. So at the end of year 0, the first gnome emerges from a magical tree on a mystical island. In each subsequent year, each gnome produces 3 new gnomes. Additionally, the magical tree on the island produces 1 new gnome each year. However, in year n, after the new gnomes are produced, a gnome-eating troll devours n gnomes. No gnome ever dies unless it is eaten by the troll. So the first part A, is to write a recurrence relation with initial conditions for G sub n, which is the number of gnomes on the island at the end of year n. All right, so easy part, our initial condition, G0, that's directly told to us at the beginning. At the end of year 0, the first gnome emerges from a magical tree. So at the end of year 0, we have 1 gnome. So G0 is 1. All right, so that's our initial condition. Let me do the recurrence underneath that. The Gn, we need to figure out from the rest of the problem, how do we figure out Gn from previous years? Well, let's do it in kind of a systematic way. Let's think about the start of year n. At the beginning of the year, we have all the gnomes that survived the previous year. So that's Gn minus 1. Every gnome that was alive at the end of the previous year is alive at the beginning of the next year. Then each one of those gnomes is going to produce 3 more gnomes. So we're going to gain 3 times Gn minus 1. Okay, so these are the gnomes that we started with at the beginning of the year. These are the gnomes that they produced. Then we've got the magical tree. it makes one new gnome, so that's plus 1. And then the troll comes along at the very end and eats in gnomes. So we're going to lose in. So we subtract in from that. Okay, so now let's simplify. Gn equals 4gn minus 1. We'll say minus n plus 1. Looks a little bit better, I guess. So there's our recurrence. There's our initial condition. I just need one initial condition because I only used the previous 1 year in my recurrence. Okay, so now part B is to solve the recurrence that we just came up with. So let me rewrite it. G0 is 1. So this is like a full problem. It poses a counting problem where we have to come up with the recurrence. Then we have to completely solve that recurrence to come up with the formula for our counting answer, our gnome answer. Okay, so let's look at the recurrence first. This is non-homogeneous because it's got this extra function at the end, but it's just a linear recurrence. In fact, it's a very simple linear recurrence, a degree 1 linear recurrence. So our first step is to come up with our characteristic equation for the homogeneous version of this. That's degree 1, so it's going to be r to the first minus 4 equals 0. So r equals 4 is our root. That means my homogeneous solution, AHN, is just going to be alpha times 4 to the n. So let me put these ingredients off here to the side. Alpha times 4 to the n is our homogeneous part. Then we need our particular solution. So APN, this is just like we did on problem 2. Well, our function is a polynomial. It's degree 1. So my particular solution is going to be a degree 1 polynomial, an plus b. The exponential part's just 1 to the n. 1 is not one of our roots, so this is it. I just have to leave it like that. That's my particular solution. But since we're actually solving this, I have to figure out what a and b are. So what I'm going to do next is, let me tentatively write my particular solution over here. An plus b. So I can erase all this. To figure out a and b, I'm going to plug APN. I guess I should be using g's. Well, it's fine. I'm going to plug APN into my recurrence. So GN is going to be replaced with APN. So I have AN plus B equals 4, but now it's n minus 1, so that'll be times A times n minus 1 plus B minus n plus 1. Remember, when we're plugging the APN into the recurrence, we leave this last function the same. We're not plugging anything there because our sequence only appears where there's the letter with the subscript. Okay, so now I have this polynomial equation that I need to multiply out so I can match my coefficients. An plus b equals 4an plus 4a negative 1 is minus 4a plus 4b minus n plus 1. So if we look at the n coefficients, I have an equals 4an minus n. So that's going to tell me negative 3an equals negative n. So 3a equals 1, a equals 1/3. Let me tuck that off to the side here. A equals 1/3. To find b, I look at the constant coefficient. so the constant term. Well, on the left side, I've got b. On the right side, the parts that don't have any ends, I've got negative 4a plus 4b plus 1. Let's subtract. Let's do it like this. Let me get the a's to this side. 4a minus 1 equals 4b minus b is 3b. 4a is 4/3. Because I know a is 1/3, so 4a is 4/3. That tells me that 4/3 minus 1 is 1/3 equals 3b. So b is equal to 1/9. All right. So almost done. So now our solution for Gn, it's our homogeneous thing plus our particular thing. So let me do the particular first. It'll be 1/3 n plus 1/9, then plus our homogeneous solution. That's alpha times 4 to the n. So this would be the collection of every sequence that satisfies this recurrence relation. Now we want to make it so it satisfies the correct initial condition. So that's just plugging in n equals 0 and solving for our unknown alpha. So G of 0 is supposed to be 1. If I plug in n equals 0, 1/3, 0, 0, I get 1/9. 4 to the 0 is 1. So alpha is going to be 8/9. So our final answer then is this sequence. All right, so that's a complete sort of problem where you have a counting problem, you set up a recurrence. This one turns out to be a relatively easy recurrence, but you set up a recurrence, then you use the techniques that we've developed to solve that recurrence. If you're asked to do one that is the entirety of this type of problem, the recurrence that you end up with shouldn't be that long or difficult to solve. So this was just a degree 1 recurrence, and so it was relatively short. All right, so that's it for this quiz. Like I said, if you have any questions or need extra clarification, send me an email and we'll try to figure it out how to answer it.